all, thank you very much for organizers and for Professor Spuklik for the very nice conference and for giving me second talk. And today I'll present the dynamic motion of electric current carrying string loops around magnetized black holes. It is a continuation of the work which yesterday has been presented by Martin College, and it will be done in this group. We will extend this research to the magnetized black hole cases. Okay, the outline, the content of my presentation is the following. We will first discuss the dynamics of the string loop in combined gravitational and magnetic field, consider some conserved quantities. We will study the boundaries of the motion of string loop, and we'll look to the very interesting effects such as the transmutation effect. So what has motivated us is that nowadays, as we know, there is no any strict mathematical or physical model which can properly describe the motion of the and creation of the relativistic jets. So, but it's generally believed that such relativistic jets create due to the interaction of the external magnetic field with the accretion disk around the compact object. And these magnetic fields play a very important role in such processes, joined with astrophysical black holes, in such process of the particle acceleration, the mechanism of the energy transfer from accretion disk to jets, the jets collimation, and we here consider some toy model of the plasma that could be described as a one-dimensional string loop. And before studying it, we will first little concentrate about the magnetic field. So in our approximation, we use weak magnetic field in such sense that it doesn't change the gravitational background. So the metric of the space-time is the same as in non-magnetized case. And for doing this limit, we can use the energy of the electromagnetic field, which is order of square of the strength of the magnetic field, and compare it with the gravitational energy of the cosmic object, and we will obtain some maximal value of the magnetic field, which changes the gravity such as it changed by the mass. So in our approximation, our field is weak in this sense. So we use the simplest case of the black hole, namely the Schwarzschild black hole, and the magnetic field is uniform and homogeneous at special infinity, and in such case it describes by the four-vector potential of the electromagnetic field, and in this case it has only non-zero component A phi. So let us go to our model. So it is a schematic picture of the string loop. We have some string loop, which is initially oscillates near close region to the black hole, and it can freely oscillate, changing its radius, and can move along the axis of the black hole. And here we have some electric current on the loop and the external magnetic field. So since we have this external magnetic field and the current, we have some Lorentz force which act on the string loop, changing its radius. And it is necessary to say that our string loop always preserves its stability and axial symmetry. We will discuss why we can really assume that our string loop always stable, and but first, since it's if we assume that it's always stable, we can choose only one point on the loop, and it's the motion of this point can describe the whole string movement, which can be described in this string trajectory plane, which is shaded here. So I will not talk long about details, because yesterday there was long discussion about it presented by Martin College. I will just say that our string loop can be characterized, so we can introduce some world sheet, and the dynamics of the string loop will be described by the action, and it by the parameter of string tension mu and some scalar field. So gradient of this scalar field will give us some current, and using the symmetry of the space-time, one can introduce space-like and time-like the Killing vectors, which correspond to the
index, yes?
sorry.
Yes.
Sorry, it is a mistake. Sigma is the index here. Yes, and
This is index.
yes, this is index. Sigma is index. Yes, it comes from the string world sheet because it can be described by only two components, sigma and tau. So these Killing vectors correspond to the energy and angular momenta of the string loop. And before studying properly the dynamics, let us make clear some properties of the string loop. So we can, for being it more evident, we can compare the string Hamiltonian as a flat space-time with the string with the Hamiltonian of a particle, of the charged particle in the flat space-time in the presence of the magnetic field. So we can see that these three terms are completely similar, and these two terms in blue frame looks very similar. So for the particle, when we have the angular momentum, we can say that this new parameter J can be described as the angular momentum of the string loop, and these two terms related to the Lorentz force. So it is an interaction between the electric charge and the external magnetic field, and in the case of the string loop, we also have these two terms, which is related first to the string tension and the external magnetic field component. So the corresponding Hamiltonian in Schwarzschild black hole space-time will have this form, and where the effective potential is written in here. So let us look more properly to the old terms of which consists the effective potential. So here Fr is a lapse function. It's due to this Schwarzschild space-time metric, and but in the bracket, the first term corresponds to the energy, the pure influence, pure contribution of the energy of the external magnetic field. So as we know, the energy of the electromagnetic field is the square of the strength of the field and its volume. So the second term corresponds to the interaction between charge and between the current and the external magnetic field. So it's somehow related to the Lorentz force. So it's the interaction between these two things. And the third term, it's the pure contribution to the energy from the string. So pure contribution of the string loop motion, and it depends only on its angular momenta. So, but this effective potential doesn't consist the self-magnetic field, because we know that the presence of the current should create also the self-magnetic field on the loop. But why it is not included here? Because we can easily estimate the self-magnetic field and can show that it is extremely small. So it is negligibly small in comparison with the external magnetic field. So for some normal values of the current and other parameters of the string, we obtain in 10 to minus 3 Gauss as a self-magnetic field strength, while for comparison, the external magnetic field near the stellar mass black holes can have the value 10 to power 8 or 10 to power 4 for supermassive black holes. But of course, the self-magnetic field plays some important role in our assumption. As I said in the beginning, it helps to stabilize the string loop relatively to the axis of the black hole due to the interaction of the self and external magnetic field. So there appears some moment which preserve its stability. So using the effective potential, one can find all possible types of the trajectories. Here we have four types of the motion of the string loop. By red lines correspond to the boundaries of the motion. For example, if the string is located somewhere here, it can, for the first case, it can fall onto the black hole or can be accelerated to infinity. So it is open trajectories. In the second case, the string always will fall onto the black hole. And the third case, very interesting, and the string loop cannot go to infinity or cannot be captured by a black hole. And the fourth case, which is the most important for us, when the string loop will not fall onto the black hole, but will go to infinity. So first and the fourth cases are more important for our motivations. So of course, the final stage of the string loop will entirely depend on its angular momenta. I will not look a lot for the details, but I just say that here we have two possibilities when the electric current is negative or positive, which means that difference only in the direction of the current, and the shaded region correspond to the stable trapped states of the string loop, and with increasing of magnetic field for the negative current, we see that the trapped states increase, while for the positive current it decreases. So it's again some details, but we will skip some these details and the calculation. I just say that we found all the limitations when it can go, it can change all its types of the motion and all the critical parameters. So, as I said, for our motivation is more important whether the string loop escaped to infinity. And for finding this limit, we should use the limiting energy in the flat space-time. So, if the particles, if the string loop's energy is higher than its energy in the flat space-time, it can go to infinity. In another way, it will be trapped or will be captured by a black hole. So, so here we can see some representative picture. Let us take our string loop in some point with some values of the parameters, which doesn't matter. We just take the string loop at some point, and we'll look its evolution when we increase our magnetic field. So we see in the first picture, if the string loop starts its motion near the region of the black hole, it falls onto the black hole. So the captured. Then we little increase our magnetic field, and we see that the boundaries completely changed, and now the string loop is trapped at some region. Then we also again little increase our magnetic field, and we see that the boundaries become open to infinity. And in the fourth case, when we again increased our magnetic field, we see that after several jumps it goes to infinity with a very large velocity. So this case corresponds to the string loop string transmutation effect, so-called. So what is it? The string energy can be decomposed to two components, to its string oscillatory energy and the string linear motion. So the energy conversion between the oscillation and the linear modes of the energy we call the transmutation effect, and the minimal energy in x direction in flat space-time is very important, because in the flat space-time, when there is no any forces, it has only oscillatory energy and doesn't have the linear mode energy, and in the flat space-time, this is unconvertible energy for the absence of the magnetic field. So, but when we introduce the magnetic field, we see that this energy become more complicated, and it starts to depend on the electric current and on the magnetic field. And we can find for this case the Lorentz factor, which is equal to the total energy divided to its energy at the flat space-time. And the Lorentz factor is maximal when this energy, flat space-time, is minimal. So we can even obtain some maximal acceleration when this term is minimal. So of course this effect works also in another direction. So string loop can be not only accelerated but also decelerated. So and there exists some critical magnetic field for which the high-speed acceleration is possible. So in principle, this term of the flat space-time can be equalized to zero, and it corresponds to some critical magnetic field, which depends on the current of the loop and the angular momentum of the loop. So let us again say about our main results. So the magnetic field, we showed that even very small can completely change the character of the string loop motion. And the string self-magnetic field can be negligibly small, but it helps us to preserve its axial symmetry. And the external magnetic field helps to the string collimation due to some transportation effect. And the magnetic field may change the type of the trajectory, as we see. Or we can, changing the magnetic field values, we can go through all ranges, all possible types of the trajectories of the string loop, and there exists some critical value of the magnetic field for which the oscillatory motion totally vanishes, and in this case the Lorentz factor can take the arbitrarily large values and for some properly chosen values of the magnetic field and electric current on the loop. Thank you very much.